In this video, we're going to cover the Bohr model of the atom, which is a way of explaining atomic structure. And it grows out of two things, really, at the start of the 20th century. And what we needed at that time was a model of atomic structure that explained two recent results, two things that people had recently learned about samples of pure elements. First off, any model of atomic structure had to explain and had to take into account Rutherford's gold foil experiment. And remember that Rutherford did an experiment where he shot alpha particles through gold foil, and he found out that the vast majority of the alpha particles went straight through the gold foil without anything happening to them. And so the conclusion from that is that most of the atom is empty space. And the only thing that's not empty space is a massive positively charged nucleus at the center. So the protons are in the middle. The second thing that our atomic models have to explain is how light interacts with atoms, right? Remember we saw these discrete spectral transitions. When I do atomic emission or atomic absorption spectra, I see lines, not a smear of light. And so there are defined transitions. And so what we know about that is that the nucleus is at the center. That's what the gold foil experiment says. The electrons are somewhere outside, and they're the ones that are responsible for producing these spectral transitions. And so these two things are really the jumping off point for Bohr, who worked for Rutherford, by the way, at the time, for defining atomic structure. So the first assumption that Bohr had to make for his atomic structure was that he was going to start with Coulomb's law. And remember, Coulomb's law describes Coulombic potential energy. So I have a positively charged nucleus. I have negatively charged electrons on the outside. We're just going to talk about one proton and one electron right now because that makes it simple. And remember, I could also estimate the amount of force involved there. And that force is what's keeping the electron and the proton bound to each other. Remember also that that's why the atom's holding together, right? We're staying bound together. This is a negative force and a negative Coulombic potential, right? Because I have a negative thing attracting a positive thing. So sign-wise, we're looking at negative numbers. We're not talking about repulsive force. And it's distance dependent. Remember, the closer the electron is to the center, the stronger the attraction. The farther away, the weaker the attraction. In order to explain why we had discrete lines in the spectrum of hydrogen, so why we saw those single lines and not smears, Bohr said that electrons could only travel in quantized orbits, so they could only be at orbits at fixed specific distances from the nucleus. The second thing that he said was that those orbits have fixed energies, right? If they're fixed distances, they are fixed energies. The third thing he did was he gave arbitrary numbers, integers, 1, 2, 3, etc., to orbits. The closest orbit he called 1, and then any higher number was successively farther from the nucleus. Sounds a little bit like Rydberg's equation, doesn't it? And so that's a good sign. It's starting to sound like something they already knew. In order to deal with the emission spectrum, which remember said that the lines were getting closer together as the wavelengths got shorter and shorter, Bohr said that the energy levels are unequally spaced, right? They get closer together as the n gets larger. Also, to explain the spectral transitions, what Bohr said was, if I look at an electron, a transition happens when light is absorbed by an electron. So light comes in, the electron absorbs it. We're looking right now at an electron in the ground state, which just means it's as close to the nucleus as it can possibly get. What that light can do is it can promote an electron. So I moved from a 1 to a 2. Right? That's called an excited state. I'm not as close to the nucleus as I could be. Now, there's no reason it has to go from 1 to 2. It could go from 1 to 3. It could go from 1 to 4. It could do anything that it wanted to do. It just starts in 1 and it goes to some other excited state. Eventually, that electron's going to have to fall back down. So it falls from 2 back to 1. And we call that a relaxation. It was promoted. It was excited from ground to excited state. It relaxes from excited back to ground. And when it does that, it gives the photon back. And that photon corresponds to the lines. And by the way, Bohr said, well, this red line is the relaxation from 2 to 1. This first kind of periwinkle blue line is the relaxation from 3 to 1. This would have been 4 to 1, 5 to 1, and so on and so forth. And so with this orbit model, Bohr took both of those results that we needed to take into account. He used Rutherford's result that the proton was at the middle. He used the emission spectra result that there were discrete spectral transitions, and he said that there are these orbits that must explain what the electron's doing in the model of the atom. Let's take a look at a couple of general trends that we see in the Bohr model as well. The first one is, let's think about transitions and what the highest energy transition would be. So we've got three possibilities. We could drop from 3 to 1, we could drop from 2 to 1, or we could drop from 4 to 1. Which one of these would involve the highest energy? Take a minute to think about it, and then pause. I'll wait, and we'll see if you got the right answer. I hope you thought that the transition from 4 to 1, the biggest drop, would correspond to the highest energy. And in fact, it does, right? Anytime I drop a larger number, then I'm going to end up with a higher transition energy. Let's try another one. Which transition results in the longest wavelength? And I do want to remind you, remember, wavelength and energy are inversely related. Big energies are short wavelengths. So take a moment to think about that and come back. Good. I hope that you got that the short drop would be a short wavelength. Let's try to solve some problems about where the transitions would be. So let's calculate a photon energy to transition from n equals 1 to n equals 3 in the Bohr model. And particularly, I want to remind you that if I'm having a transition between these two integers, the Rydberg equation still applies to the Bohr model, right? The Bohr model was made to take into account the Rydberg equation. And so I'm predicting a wavelength because that's what the Rydberg equation gives me. I use my R. And I arrange my 1 and my 3. My only goal here is to get a positive number out of this so that the whole answer is positive. So I find that my lambda, right, remember I solve for 1 over lambda and then I take the reciprocal, ends up being about 102.6 nanometers. This is a good time to note that if you looked at a spectrum, the electromagnetic spectrum, you'd find that 102 nanometers is UV. But we aren't quite done with this problem because we asked for the energy of the photon and we're still at wavelength. And we can just go back to our original light equations. If I know wavelength, I know energy. And so I can solve for that and I can find that my energy of that photon is about 1.9 times 10 to the negative 18 joules. What else can I do now? I can calculate the energy that's required to do what's called ionizing the hydrogen atom, right? And what ionizing means is that we're actually going to take that electron, and it's in its ground state, so it's starting at n equals 1, and we're going to take it off of the atom. We're going to break the energy of association, the energy of attraction between the positive nucleus and the negative electron. That's number-wise basically saying we're going to transition it to n equals infinity, so some very, very, very large n way out there. We can use the Rydberg equation for that, right? We can say that we're starting at 1 and we're ending at infinity. And since 1 over infinity, 1 over a very, very large number squared, is basically 0, then I'm basically taking the Rydberg constant times 1. And when I do that and I solve, the lambda is about 91.16 nanometers. So what that means is, energy-wise, I have a photon of about 2.2 times 10 to the negative 18 joules. If I put in a photon with any higher energy than that, I'm practically knocking the electron off of the atom. I'm ionizing it and removing it from the atom. And the Rydberg equation, which fits with the Bohr model, helped me to figure that out. So we have this model, and we know that it at least does what it's supposed to in terms of taking into account the Rydberg equation for discrete spectral transitions and Rutherford's gold foil experiment for the position of the nucleus. Our question is, does it work really well past that point, though? And as far as advantages, the Bohr model works perfectly for the hydrogen atom. It can do anything you need for explaining hydrogen, and it explains ground to excited state transitions. So when I start from 1 and I move up, it explains everything about how that works. The disadvantage is that if an atom has more than one electron, the Bohr model fails. I can't use the Bohr model to explain anything as simple as helium. Anything harder than hydrogen is not doable. Why? Well, it turns out, as we're going to be talking about shortly, that the nucleus treats multiple electrons differently. It's not like it sees two individual electrons. It sees some sort of aggregate. And that's because the electrons are interacting with each other. When I have two electrons, it's not just that the positive nucleus is talking to the negative electron, but I might have two negative electrons talking to each other. There's attraction between the nucleus and the electrons. There's repulsion between the electrons. The last thing that's a problem with the Bohr model is that orbits are simply too simplistic. It is not a planetary, the planetary explanation of electrons doesn't work. It's not like having a moon around the Earth or a planet around the sun. That circular orbit is too simple. And Bohr did try to fix that. He did try to say, well, what if the orbit's an oval or something like that? But orbits turn out to be three-dimensional and very, very complex. And so though the Bohr model is a really good starting place, it's not the place that we need to end up when we want to describe atomic structure.